Hi everybody, welcome to the first of a series of videos that demonstrate the use of the SWL Tools spreadsheets. I'm Mark Decay and I'll be giving you the tour. I developed the SWL Tools spreadsheets to help with the calculations and the methods that are found in Sun, Wind and Light Architectural Design Strategies 3rd edition. A book that's used around the country by schools of architecture and by professional offices to help with the design of sustainable buildings in the preliminary design phase. As you may know, Sun, Wind and Light is a design resource that helps to design energy efficient buildings, in particular using on-site resources of sun, wind, and light. The 3rd edition is focused on net zero energy buildings and carbon neutral buildings. And the SWL Tools spreadsheets are particularly focused on helping you to do the calculations that are involved in understanding the performance of the buildings from these perspectives of carbon neutral and net zero energy. All right, let's take a look at the first worksheet.
Now I'll click on P1 Energy Targets in the tab at the bottom to bring up our Energy Targets page. The labels P1, P2, and so forth refer to the individual sections of Part 7 high-performance buildings that are found in Sun, Wind, and Light. It's a good idea to read the associated sections either before or after viewing each of these videos and before moving on to the subsequent sections of the worksheets. The P1 Energy Targets worksheets ask you to do 3 things: to input some building information, to input some information about design temperatures, indoors and outdoors, and to choose an energy target. The cells that are colored in green indicate places for user inputs, and the white cells are calculated by the spreadsheet based on your inputs. Results are often shown in bold for emphasis. Note that each section has a corresponding instruction on the left. The instructions are shown on the left on this page. In other worksheets, they may be on the left or on the right. The instructions will tell you where you need to get information that you need to input into the spreadsheet. For this course, all the necessary information will be provided, either in Sun, Wind, and Light itself or in additional resource documents. And then finally, there's some terms that you'll notice listed in all caps, and most of those refer to particular analysis techniques or design strategies or high-performance building assessments that are found in Sun, Wind, and Light. So these are the names of individual sections within Sun, Wind, and Light. Okay, let's take a look at the first section, that is to input some building information. So I'm going to select the occupancy type from a menu. Notice if I click on this under occupancy, I get a little menu, and I can choose residential or non-residential. I'm going to stick with residential because we'll be looking at a house in this example. Also note that the instruction is given on the left. So just over here on the left side it says select occupancy as residential or non-residential from the menu. So these instructions follow a kind of logical order that parallels what you need to do in the spreadsheet. So the name that's referred to here in bold as occupancy, notice that it shows up on the right as the title for the piece of information that you're trying to input. Also on the right here, it's called occupancy. So next I'll input the floor area and the conditioned volume. The example we're going to use is a small house, and its floor area is 1,472 square feet. And right now we haven't really looked carefully at the volume, but I'll assume that it's about 10 feet on average with some high ceilings and so forth, because we'll be thinking about stack ventilation later. So I'm going to call that 14,720 cubic feet. And let's take a look at what that little house looks like so you know what we're doing. The site for the house is a generic inner ring urban neighborhood. It's on the grid. It has an alley in the back. Its long side faces south. And this is the study from which the floor area and the volume are taken. There's an outdoor room in the middle that serves as a breezeway, and it also has an extension to the south for winter sun. There's some street trees to the east that create some shade in both the summer and the winter. So these are some shadow studies for this little house, and they show a relatively long and sunny south exposure. So we're setting ourselves up to work well for passive solar in one of the later worksheets. And there's also enough room on a sunny south-facing roof for PVs in case we need them later, and of course we will. So here's the site plan view that shows the outdoor room open to the breeze in the summer. That's blue in the lower plans. And with the aid of a sliding door to the north, the outdoor room is also protected from the winter winds. That would be the red area shown in the upper plans. So next we'll input some design temperatures. This will be a passive building, so it's going to have a relatively wide comfort zone. I'm going to set this at 65 degrees for the low temperature in the winter and 80 degrees Fahrenheit for the high temperature indoors in the summertime. Now, if you choose a narrower comfort range, which is more common in non-passive buildings, then the building systems would have to be larger and the mechanical systems would run more hours, and in a passive building, the passive systems themselves would have to be larger. So it turns out indoor temperatures are actually one of the biggest choices that you have in affecting energy use. Now, when we get to latent cooling a little bit later, the indoor and the outdoor wet bulb temperatures are also important. So you can find the wet bulb temperature by using a psychrometric chart, but I'm going to use an online calculator. And over here in the instruction, it tells you where to find one of these. There's several online. This one is from the Linrick company. Let me pull that up. Here's an online calculator for the psychrometric properties of air. So I'm going to say that it's 75 degrees inside, and let's make it about 70% relative humidity. And in Knoxville, the altitude is about 650 feet above sea level. So I'm going to click on Calculate, and here's my wet bulb temperature. Notice that's just about 68 degrees. So let's remember 68. I'm going to close this. I'm going to go back over here to Indoor Summer Wet Bulb and call that 68. Okay, now we need to look at our outdoor temperatures. To find the outdoor design temperature, we have to go to a good source for climate data. I like the engineering weather data files, so let me pull that one up. Here's the engineering weather data file for Knoxville. These are developed by ASHRAE, and they're available in a CD from the National Climatic Data Center. They're also public domain, so we've included them on the Sun, Wind, and Light electronic. You can also use other sources for the same kind of information, such as the ASHRAE Handbook of Fundamentals. Now in the summertime, I'm going to choose a 1% design condition, and that's going to give me 90 degrees for outside. So what that means is 1% of the time, it might be hotter than 90 degrees. I'm going to also design for the 99% occurrence in the winter, and that's 18 degrees in Knoxville. So 99% of the time it will be hotter than 18 degrees. That's what that means. So for the same 1% condition, if we go down here into the wet bulb territory, the 1% occurrence for the wet bulb in Knoxville is 76 degrees Fahrenheit. So let's remember those three numbers, 90, 18, and 76. I'm going to close this, and I'm going to go back to our spreadsheet. So outdoors in the winter is 18 degrees, in the summer 90 degrees, and the wet bulb 76 degrees Fahrenheit. So that's it for setting our indoor and outdoor design temperatures. Now these get used in various ways to calculate heat gain and heat loss, and latent heat transfer, and so forth in other spreadsheets. The last thing we need to set on this page is your energy target. For this, we'll refer to P1 Energy Targets, the section from Part 7, High Performance Buildings in Sun, Wind, and Light. So let me pull that up. Now I've zoomed in here on the actual table that we need. Since we're doing a residence, I've selected the table for energy use intensity targets for U.S. residential buildings. These show the regional averages for building energy use. Now we are in the South region here in Tennessee, so I'm going to go over and look at South and pick single family detached, which is this row. So the median building, that's a single family detached residence in the southern region, uses 40 kBTUs per square foot per year of energy. So what that means is 40,000 BTUs per square foot of floor area in a year. That's the typical rate of energy use. Now the table also gives us a 70% and a 90% reduction factor if we wanted to just pick those targets right off. So let's take that 40 and I'll show you what we do with that in the SWL Tools spreadsheet. So over here under Target Fossil Fuel Use, I'm going to put in 40. And notice that all of the values down below get recalculated. Once we've set this average value, the worksheet calculates all the Architecture 2030 targets. So notice if we want to do an Energy Star building, which we don't recommend, that's only 25% less. If we want to cut 50% of the energy use, that would be the 2005 target from Architecture 2030, and we'd be looking at using 20 units. Today, we'd be looking typically at doing 70% less. That's the 2015 target just around the corner. That target would be 12 units of fossil fuel energy, everything measured in kBTUs per square foot per year, all the way down to 0 for the carbon neutral net zero energy building. Notice that you can then choose what your target would be. So maybe I'll choose 80% or 90%. In this case, I'm going to let it ride at carbon neutral net zero energy because that's what we're trying to design for.
Well, that's it for the P1 Energy Targets worksheet. For more information about energy targets, make sure to read Section P1 Energy Targets in Sun, Wind, and Light. In the next video, we'll see just how easy it is to calculate quick heat loss in preliminary design using Sun, Wind, and Light and SWL tools. See you there!